Ever wondered what makes up the mathematical backbone of computer science? Real sequences and series provide the answer. These concepts are fundamental in elementary mathematics and crucial for advanced topics. Now, what exactly is a real sequence? Well, it's simply an ordered list of real numbers. For instance, consider the sequence 2, 4, 6, 8, 10, where each term is twice the preceding one. So a real sequence is nothing but an ordered list of real numbers like the sequence 2, 4, 6, 8, 10. Sequences, like the characters in a book, have their own behavior. They can converge or diverge. When we talk about convergence, we mean that as we go further down the sequence, the terms get closer and closer to a specific value. Let's take the sequence 1n, for example. As n increases, the value of each term gets smaller, approaching 0. This sequence is said to converge to 0. On the other hand, divergence refers to a sequence that doesn't settle down to a particular value. The sequence could keep increasing or decreasing without bound, or it could oscillate between values. Consider the sequence Hlarn. As it increases, each term just gets larger and larger with no end in sight. This sequence is diverging, it does not have a finite limit. Understanding these behaviors is key to grasping the essence of sequences and series. So the sequence 1n converges to 0 as n goes to infinity, while a sequence without a finite limit is said to diverge. If a sequence is a list, then a series is the total of that list. Now let's dive into the concept of a real series. Simply put, a real series is the sum of the terms of a real sequence. If we have a sequence denoted as _n-ing, the corresponding series is often represented as say n. This symbol, sigma, signifies that we're adding up all the terms of the sequence for all indices. Just like sequences, series can also behave in two distinct ways. They can either converge or diverge. A series is said to be convergent if the sum of its terms reaches a finite value. On the flip side, a divergent series either has an infinite sum or no sum at all. This behavior of convergence or divergence in a series is intimately connected to the behavior of its underlying sequence. So, a series converges if it has a finite sum, and diverges if it has an infinite sum or no sum at all. Now, how does all this play out in the world of computer science? The relevance of real sequences and series is evident in areas such as algorithm analysis and numerical methods. For instance, summation of a series can represent time complexity of an algorithm. If the series converges, the algorithm executes in finite time. In numerical methods, iterative algorithms utilize sequences while Taylor series expansions approximate functions. So, a good understanding of sequences and series can give us insights into the time and space complexity of algorithms.